Uh, yes, good morning, everyone. My name is Vishal. I'll be coordinator from this session onwards for another 2 months. And for today's session, we have types of sterilization and sterilization decision by Mr. Viresh Kumar H. Seth. Sir, you can start, sir. I guess everyone are there, right?
Yes, sir.
Yes, sir.
Okay, thank you.
Okay, right. So, good morning, everybody, and welcome back to a session. Pleasure to be back again. So, we're going to talk about types of sterilization and sterilization decision tree, which would be the first two sessions, and then we are going to also talk about the type of autoclaves in the third session today. Uh, so, regulatory overview. I'm not going to spend too much time here because we have already seen this slide before and we have discussed this, that it is very important for any sterile manufacturing process to ensure that there is no contamination and that any pathogenic material, pyrogenic material, any of those kind of contaminants which can cause harm to the patient have to be removed. So when we talk about the various sections of US FDA, whether we talk about 21 CFR 211.67, we talk about 211.84, or we talk about 211 211.84, we look at 211.68, every or 211.113, we see that there have been a lot of citations and warning letters which have been issued in the industry. So there is a need in the industry, and when you are working around that, we ensure that the sterilization processes are proper. Uh, Again, I don't want to spend too much time on this because I believe that the entire trainee team is aware about these definitions by now. Uh, we have spoken about this in the past sessions. We have shared this slide multiple times as a definition slide across when we spoke about the steam sterilization process and when we spoke about depyrogenation. So these are again kept here as a ready reckoner so that if somebody wants to have a look at it, they can look at it when studying this subject. So what do we mean by sterilization? The act or process, physical or chemical, that destroys or eliminates all form of life, that is microorganisms, is what is called as sterilization. Now, while the statement says it is an absolute action, there is always sterilization is actually stated in terms of probability. It is not an absolute reduction, but it is a reduction which is happening in a log reduction. So we were at an X value and we came down from X value to a Y value. And the minimum, as we saw in the previous slide, has to be a 6 log reduction. So 6 logarithmic scale is a 10 to the power of 6 reduction is the minimum requirement for any sterilization. Normally, there are other concepts of 12D approach and all that, which means that you go to an overkill approach and do a 10 to the power of 12 reduction, or 10 to the power of 6 ensures that 1 in a million reduction happens. Now, sterilization process, again, this slide has been discussed in the past. There are various forms of processes. We can use heat, we can use chemical, we can use radiation, we can use physical. And during the earlier sessions, we have discussed a lot about the moist heat or the steam and dry heat both. So in this session, I'm not going to talk too much about the heat-based sterilization processes because they are already covered. And we will talk a little bit about it when we talk about the autoclaves in the next session. There are about 4 sessions on the autoclave. Actually, not 4, but 6, including what we're going to do on 10th of April, where we are going to spend a lot of time on the moist heat and dry heat based sterilization processes. We are going to concentrate a little bit on chemical based sterilization processes, which involves hydrogen peroxide, ethylene oxide, ozone, radiation, which is gamma or electron beam, and the last one, which is physical filtration. We are going to deal with it on a separate session. So, today's session, I'm going to primarily concentrate on chemical and radiation based sterilization processes. However, just so that everybody is on the same page, we are talking about 4 main methods which are used in the sterile manufacturing process. One is heat, which could be dry or moist; gas, which could be ethylene oxide, hydrogen peroxide, ozone; radiation, which is gamma or electron beam; filtration, which is a physical form of sterilization. Uh, there is a fifth possibility, which is by means of bright light, but this technique has not yet reached a status where it can be considered as a standard sterilization technique. So, very bright light can be also used to do sterilization process, but this is not an established technique yet. Hopefully, in a couple of years from now, we will see this being used also as a technique for sterilization, which could be a good thing because that will then reduce uh, the chemical hazards, the heat hazards, etc., from the process of sterilization itself. Uh, the another way that you will come across in the industry that sterilization gets classified as a thermal process, which could be moist or dry heat, where you use heat basically, non-thermal process, which is filtration and radiation, because in both these cases you are not using any thermal uh, process, or you are not using the physical parameter of heat as a possible means of sterilization, and chemical, which could be gaseous or liquid sterilization methods. Okay, so these are the sterilization methods: heat, gas, radiation, filtration, and the other way is thermal, non-thermal, chemical. All right. Now let's just look at some of the biological indicators where they are used, and the D values of that. When you are using steam, moist heat, we have already looked at it, saying that it is a Geobacillus stereothermophilus, which is used. The ATCC number for that is 7953, and the typical D value ranges from 1.5 minutes to sometimes even 3 minutes at 121 degrees centigrade, depending on the type of steam and the type of media in which you are exposing this. Dry heat is normally Bacillus subtilis variant Niger 9372, also something which is used for peracetic acid, and the typical D range value in dry heat is 1 minute at 180 degrees centigrade. Ionizing radiations, or the radiations, normally are measured in terms of kilo gray, and when we measure something in terms of kilo gray, then you have to use a different kind of an indicator. Bacillus pumulis is the one which is used. The ATCC number is 14884. Ethylene oxide again uses Bacillus subtilis, but it has got a D value of 5.8 minute at 600 milligrams per liter concentration at 54 degrees centigrade and 60% RH. So now, if you look at the way in which the D value is being specified, in case of heat, it is always based on temperature. In case of ionizing radiation, it is the concentration of the beam, which is measured in terms of radiation energy. Ethylene oxide requires 3 parts, which is concentration, which is expressed in mg per liter, temperature, and RH. Okay, vapor phase hydrogen peroxide again uses Geobacillus stereothermophilus 7953. The D value there is not defined there because it depends on the load, and it's again one of the factors that I'm going to bring here is that in the recent timelines, vapor phase hydrogen peroxide is considered as a decontamination method and not a sterilization method. However, it is capable of reducing 10 to the power of 6 log reduction in terms of the initial bioburden. And that's what makes it still popular in the industry as a point of use. When we discussed isolators, we covered vapor phase hydrogen peroxide, and isolators are one area where vapor phase hydrogen peroxide is used even today, very, I would say, broadly and industry wide as the means of creating a decontamination within the isolated chambers. Peracetic acid is no longer used, but used to be one of the sterilization processes, which was also used very frequently in the industry earlier. But now, if we look at it, we are only talking about steam, dry heat, ionizing radiation, which would be mainly gamma radiation, ethylene oxide, vapor phase hydrogen peroxide. Again, ethylene oxide is being slowly phased out because it is a carcinogen, and we will talk more about it in the later slides today. Now, before we get into the discussion of what is the different methods of sterilization, let us understand a little bit about the death kinetics. So, how does a microbial cell kind of die? Okay, like any living organism, right? There is a initial phase where you are just getting formed, which is nothing but it's a lag phase called as a lag phase. Then there is a growth phase, which is exponential. Then you become stationary, and then there is a death phase. So these are the four phases of a microbial growth from start to finish. So what happens is that in the initial stage, if you look at it, the growth in cellular duplication and multiplication growth is plotted logarithmic because this growth is highly exponential. We all know that bacteria, if you leave it in a right media, can multiply almost to double within less than 3 to 4 minutes. Or microbial growth occurs very fast, and if you leave the plate long enough, then the entire plate will be covered with the bacterial culture or spores in no time, when the conditions are right. Leave a right media, leave a right amount of temperature for there, and you will see that the whole plate will become TNTC, too numerous to count. Now, let's understand the four phases. So when we talk about a lag phase, what does it mean? It is a means at which the cells are all in spots and places. They are just trying to survive and create a situation for themselves so that they can make a geometric progression. They are sufficient enough that you can count them on a plate, but they are not sufficient enough to start having that exponential growth. They are not reproducing very fast. Why does this happen is because they're just trying to get used to the media, to the environment. And it is like, the theory of evolution where you say survival of the fittest. So the spores which are really strong will be fighting on a survival phase, and the rest of them may not even go to that phase. So this is a small phase of lag where the microorganisms are just trying to get hold of themselves and trying to organize themselves so that they can start reproducing. The second phase is the growth phase and progresses quite rapidly, as we all know, because now these cells which are strong have got their media around them, the right conditions, and they start to multiply immediately, and at the cost of some of the weaker organisms themselves. The third phase is a stationary phase, because here at this point in time you have a media which is limited. Now you've kept these microorganisms in a plate where there is a certain amount of media. The media starts to deplete. Oxygen diffusion cannot happen because there are too many of them. The population explosion has happened, so stationary phase happens. And also because they are not able to produce, some of them die and toxic metabolites are accumulating. So this becomes like a plateau phase or the stationary phase. And then the last phase is again a death phase, where rapid death occurs. So if you leave the plate long enough there, then all those cells are going to start dying unless you give them an environment where they can jump over and grow. So these are the four phases: the lag phase, the growth phase, the stationary phase, and the death phase. What we are trying to do in sterilization is to ensure that by using the right methodology, we are trying to catch them during the growth phase and kill them instantaneously so that they do not grow exponentially. So we are working in the region between lag phase and the growth phase, that you know how much it was there in the initial stage, and before they start to take this exponential path, you kill them here itself so that they never go to this and this phase. So you directly take it from the lag phase to the that phase for whatever known numbers are there. And while studying this, we are going to look at various things like what was the microbial cells over a period of time. So this is what will tell you how the growth happens. Whereas when you are going to look at the sterilization, you will look at the sterilization media, the parameters of that versus how many uh, surviving microorganisms are there when this was the initial value and this is the final value. And when you make a reduction by one log, it is called as a d value. So this is very important that we remember what is a d value. By plotting these graphs, microbiologists generally are able to predict that what is the kind of dose or the time for which you are going to be able to need what is the time you need to expose this population so that you achieve a 6 log reduction. So a very very important study is the death kinetic study, and some of the microbiologists in the trainee group will need to be doing some of these studies when they encounter new microorganisms. So when we started our careers, which was about 30 years back, there were only a few microorganisms which were known, and therefore we were happy to use certain sterilizing agents and get rid of them. Today, as we have seen over the period of time, we have seen new species of microorganisms which have been not only discovered but have started to create issues or probably have uh, come from the environment because of the changes in environment. And even the regulation now no longer just talks about E. coli and pathogens, but also says, okay, there is a species of called as Burkholdia where you need to even take care of this Burkholdia now. So as and when you discover a new microorganism which is likely to cause a issue into the patient's safety, you have to through the death kinetic studies determine what is the best way of sterilization. And we will come to sterilization decision tree, where this death kinetic curves becomes very important, because when you choose a method of sterilization, you should first of all understand the death kinetics of the microorganism and which agent would work the best for it. So this is the importance of this curve. What is there? Okay, types of sterilization. I'm again not going to spend too much time on this because we've studied this earlier. It is heat used to sterilize items, either wet heat or dry heat. Also, moist heat sterilization, also known as wet heat sterilization or steam under pressure sterilization. also referred to as autoclaving, used for sterilizing of rubber, durable plastic material, tanks, other equipment, in situ sterilization, freeze drying chambers, wherever high temperature withstanding is not an issue, right? Lethality of the microorganism depends on the degree of heat exposure, the duration of heat exposure, and the moisture, because moisture is the most important part here, which we have to take care of, right? Mechanism of action is heat destruction of microorganism occurring through coagulation of the proteins in the cell. And what are the three major steps? You have to precondition the chamber and remove all the air, replace it with saturated steam, do the exposure of heat for a given time, and then once that is over, you have to remove the steam, also sometimes remove the moisture through vacuum and release the pressure. So that's moist heat. Let's come to dry heat. Dry heat is where you don't have steam, but you use direct heat, which is here indirect methods of heat, or heated air used for it. Temperatures are generally high. Destroys the microorganism by oxidation. Basically, you heat it up so high that the microorganism swells up and then it explodes, and as a result of which there is a death which occurs. It is referred to mainly as a depyrogenation technique used for sterilization of glassware, metal parts, oils, and dry powders. Process is simple. It involves heating with filtered air and using blowers to uniformly distribute the heated air in the chamber. It is effective, the most effective method of removal of endotoxins. Materials are dry at the end of the cycle, and corrosion of material is generally not an issue. And heat exposure occurs through convection in air, requires long exposure time to kill a resistant spore organism, or very high temperatures for a specified time. So dry heat sterilization is also, like moist heat sterilization, employed as a technique today, very industry wide, and at a very high scale in sterile manufacturing. Dry heat sterilization are a backbone of any filling system, unless you're using a ready to use systems, and we will come to that little later. We have covered a little bit of it when we spoke about the single-use bags. Now, let's focus on the gas sterilization, or sterilization using chemicals. There are many gases or chemicals which have been used: ethylene oxide, peracetic acid, chlorine dioxide, vapor phase hydrogen peroxide, formaldehyde, propylene oxide, beta propiolactone, ozone. Of these, a lot of them are no longer used because they are either too dangerous to handle, or they require larger quantities, and we have found better methods in and the three methods which are continued to be used in the industry today include ethylene oxide, vapor phase hydrogen peroxide, and ozone. When I was young, and when I first joined the industry, formaldehyde was the method of sterilization, and it used to be a very tough process to do formaldehyde-based sterilization processes, or decontamination processes, and used to be really hazardous to handle these things. Of course, ethylene oxide or any gas-based system, when you use it, is going to be hazardous to human beings. So proper training is essential. Proper protective equipment or personal protective equipment are very important, and we need to have to take care that there is no leakage or exposure of these gases to the environment or to the people who are working in this. So let's start with ethylene oxide. Ethylene oxide, the formula is there on the right hand side, also referred to as ETOH or ETO. Generally in the industry, we refer to it as ETO. It is an alkalite alkylating agent, and therefore it is very potent and highly penetrating. What happens is that it's an alkylating agent, so it acts on the microorganisms and changes the entire pH within the microorganism, around the microorganism cells. We know that the microorganism membranes are osmotic in nature, and then the alkylating agent has a high penetration, resulting in the change of the pH and the death of the cell. So that's how ethylene oxide works. It's a carcinogen. It's a known carcinogen, and but however, it was an effective way of doing it, so people used it. Uh, it used to be mixed with freon as in a concentration. Uh, so it used to be mixed with freon and then used for doing the sterilization process. However, in 1996, because of the green gas effects, I mean the sorry the greenhouse gas effects, freon was banned for use. So ETO is either used as 100% or in combination with carbon dioxide. When it is used as 100%, it is dangerous because it is highly flammable as well. So this is the reason why ethylene oxide, one, it is a carcinogen. Second, it is dangerous because of its flammability, resulting into an issue of us having to look at ethylene oxide from a perspective of whether this is the only choice that we have for doing sterilization. Now, what are the factors which influence the lethality which is caused by ethylene oxide? Gas concentration, generally used in the range of 400 to 1200 milligrams per liter. Okay, when we say liter here, it would be the volume of air in which it is pumped in. So you would have to have a concentration of anywhere between 400 to 1200 milligrams per liter. Temperature is very, very important because the temperature in which the gas is pumped in has to be maintained between 50 to 60 degrees centigrade. So if you look at the biological indicator, we had looked at a temperature of 54 degrees centigrade. Relative humidity, which is also very important. Normally 35% to 80% is what is used. And depending on what RH value you can use, the biological indicator and the biological indicator, there could be a tenfold change when you change just the RH factor. So when you decide an ethylene oxide based sterilization process, and you fix a concentration of the gas because you don't want to put in more gas, either because it could permeate the media in which you have stored your material, or is harmful beyond a particular concentration to the component or the material being sterilized. uh, you play around with the relative humidity to achieve a higher kill rate. And of course, time is an important factor. The biggest problem of ethylene oxide is that it is reactive. It tends to form compounds uh, due to the presence of moisture. And then there are other components, like if you're sterilizing, let's say, husk, or you are sterilizing any powder, the chemical composition of the powder interacting with the water and the ethylene oxide can form uh, residues of ethylene oxide, which can be hazardous to people and the environment. And there is a guideline which talks about what is the quantum of residual ethylene oxide or its compound which should be present in a process after the sterilization process is over. This is defined as per ISO 10933-7 and also by the US FDA. Let's first understand the ethylene oxide cycles. First, there is an air removal in the chamber and humidification. Then there is pulsed humidification. What is pulsed humidification? You have humidified the chamber, but when you have humidified the chamber, it is possible that because of the presence of the certain amount of air or because of the stabilization, you need to adjust the humidifications so that it is stable. Then you pump in the gas into the chamber, achieve a certain concentration, and then you start a hold time. Once the hold time is completed, you do a vacuum degassing. You apply vacuum inside the chamber so that you can remove all the gas from it, and then you introduce sterile air into the chamber so that the air slowly replaces the ethylene oxide into the system. So the vacuum helps in removing any residual ethylene oxide in its form, or any volatile compounds of ethylene oxide immediately, and then the air slowly replaces it and stabilizes the material which is there. So this is how ethylene oxide sterilization works. uh, Ethylene oxide is used for a lot of powders, for a lot of solid material. So most of the animal houses where you have feed which is given to the animals which are under study, right? So that feed is generally solid. It is husk, it is grass, dried grass. Those kind of materials are used for used for feeding these animals which are under study. You can't moist heat sterilize them because they would catch moisture, and then they would, when left around, they would of course start having bacterial growth. You can't dry heat them because they can't withstand those temperatures. So generally, they are subject to ethylene oxide sterilization, and ethylene oxide sterilization ensures that it is free of microorganisms. It is then fed to the animals as a nutritious product, but at the same time free of any bacteriological contamination. There used to be a process called solid state fermentation, which was used in fermentation. It's still used in a lot of fermentation based processes for manufacture of a lot of molecules, including enzymes. And the solid substrate in a solid state fermentation used to be something like husk of wheat or wheat bran. And the wheat bran, because of the use of fertilizers and pesticides in the fields, used to have some amount of specific microbial growths, which was detrimental to the solid state fermentation, were not easy to kill through the heat, moist heat process, which was used for the sterilization of the wheat bran. As a result of this, what was done was an ethylene oxide sterilization was brought in as a process, where ethylene oxide sterilization was done on the bran. Then it was brought into the premises, and then it was subjected to moist heat sterilization before the inoculum was spread on it for growth, right? So this was one of the processes where it is used. Ethylene oxide is still used. Ethylene oxide is also used, for example, in a lot of medical devices at times where you need to kind of sterilize as a terminal sterilization process. We have studied terminal sterilization of a product using heat as a situation. You could use gamma irradiation or gas or a gas sterilization also as a process for sterilizing the end product. So ethylene oxide is used for either the incoming material or sometimes at the outgoing material. Again, as I said, not a choice of sterilization if there are other means which can be applied, because just because it is too dangerous to handle and it is a carcinogen. So what is the other material which we can use? So let's talk about gamma irradiation. and beta irradiation. Okay, these are two methods of radiation which are used. Gamma irradiation is one, and beta particles or accelerated electrons is the other one. There is a third method of radiation sterilization, which is commonly used in the laboratories, which is ultraviolet light. But over a period of time, again, ultraviolet light is not uh, considered as a sterilization process. It is more considered as a decontamination process, and also not very effective at that. So, while it continues to be used in laboratories, in certain pass boxes, in the laminar airflow units, etc., and yes, for those kind of applications, combined with the disinfectant solution, it is still effective in terms of disinfection. It is not the only means of using a sterilization of those spaces. So we're not going to talk too much about ultraviolet light, because again, from a regulatory stand perspective also, ultraviolet light is not considered as a sterilization process any longer. Gamma radiation, yes. Electron beam radiation, yes. But ultraviolet, no. Now, of the two, gamma irradiation is most widely used. Why? Because it is highly penetrative and an effective radiation method. How is gamma irradiation done? You have cobalt 60 high energy photons, which are used in gamma irradiation. So you accelerate or you energize the cobalt 60 particles, which generates the photons, and as a result, generates a radiation, which is what is used for killing the microorganisms. Beta particles, on the other hand, are like electromagnetic, are ionizing radiation and not electromagnetic, and therefore they are less penetrative. They are generally generated from a radioactive element like strontium 90 and accelerated mechanically to an extreme high energy of 0.5 to 3 mrad. Okay. Ultraviolet light is considered to be a surface sterilization method only, since its energy is not sufficient to penetrate the material. Look, very important is that for any sterilization, it has to be able to penetrate the material and be able to destroy the microorganism. Both gamma irradiation and beta are able to do it. In the two, gamma is much more penetrative as compared to beta, and therefore gamma is the most widely used radiation methods. Maybe as we go across, we could find other radiation methods or radiation techniques which are more penetrative and can replace gamma. Now, what are the items which are subjected to gamma radiation or radiation techniques? It is the same methods like plastic material, heat liable material, powders. Also, a lot of devices, as I said, the devices, single-use bags. So when we look at single-use bags, which are manufactured in a factory, and before they are supplied, they have to be sterilized, then gamma irradiation is the way of doing it. You can't dry heat them, you can't moist heat them, because both of them will destroy the plastic material. So gamma irradiation is a methodology which is used. You could use an ETO, but gamma is much more safer, and therefore gamma is used. You have a lot of products, injectable products, which need terminal sterilization, and the best methodology for terminal sterilization of some of these products is again gamma irradiation. A lot of times when you assemble a device, a device which is used, because now people use self-administration techniques, or even the doctors use devices with a dose to administer the medicine to a patient. They use devices, and those need to be again sterilized, sometimes post manufacturing, and there again gamma irradiation is a technique which is used. Any material which is heat liable, radiation is a good technique for it. And a powder, you see, you cannot subject a powder to dry moist heat because of obvious reasons, that it will mix with the moisture and change its properties, or sometimes even dissolve out. You can't subject the powders to very high temperatures because there is a fear of burning, or the charring of the powder itself. So again, you use radiation sterilization techniques, or you use ethylene oxide. But as I said, gamma irradiation is a preferred methodology. A lot of solid materials are in that category. Here, though, I have written only powders, a lot of solid material would come. How does it act? It When you have a particular radiation dose and expose the microorganism for sufficient time, then it damages the nucleoprotein of the microorganism, as a result of which the kill is achieved. When doing radiation sterilization, an overkill approach is always used. We, instead of aiming for 10 to the power of 6, we use 10 to the power of 12 log reduction as a factor for determining the effectiveness of a gamma irradiation or any kind of a radiation, and therefore it's always an overkill approach. You determine the most resistant microbial spore form, and then you subject it to a gamma irradiation, which leads to a 12D kill. So that is how you measure it. What you see on the right hand side is a typical equipment in which this radiation is carried out. So there is a conveyor belt in which the material is fed into the system. It enters into a conveyor system and goes through various twists and turns, where in between these two you will see that the gamma radiation is done. So there is an electromagnetic radiation which is created between the two sections here while the material is passing through that. It keeps on going back and forth, back and forth, back and forth, and then at the end of it, it comes out into the final product. So by determining the length of the chamber and the number of times that it gets exposed to the gamma radiation, you are achieving a 12D kill approach. This is a chamber which is made out of proper concrete or non-penetrating material, because you do not want that radiation to come outside and therefore harm the environment or the people who are around it. And therefore this is generally made out of either concrete, or for very large chambers, permanent chambers, this can be made out of concrete. Otherwise you use very thick materials, metallic frames of stainless steel with some lead panels which are on the outside to protect, so that there is no penetration. Very similar to what you use for radioactive containment. So these chambers are widely used. Again, you won't find these chambers in manufacturing facility. These are third-party manufacturers or third-party service providers who will uh, who will generally keep a facility of this size, and you will send the material to them, and that material, when it goes to the vendor, he will gamma radiate it and send it back to you. Because you cannot, first of all, you may not have sufficient material or quantum to gamma irradiate every day, even if you are manufacturing a batch every day, because this investment on this equipment is very, 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 very high. And therefore, when you have to sterilize, when you have to invest in a gamma irradiation facility, you should be doing multiple batches a day to make this cost effective. as a result of which you will not find these in the industry. So if you go to a injectable or a sterile manufacturing facility and say, I want to see where the gamma irradiation equipment is, then you will be asked to go to a third party and generally not on premises, because one, it is expensive, two, it needs special skills to run this, three, the volumes in a plant are generally not sufficient to support these kind of infrastructure within the site. So there is an industry called microtrol which does this as a business. They have facilities all across India now, where they do this as a third party service to industry. Okay. Though I said I'm going to cover filter sterilization in a different session, I'm going to talk a little bit about filter sterilization here, because I'm talking about different types of sterilization, and therefore you should have a clear picture of the entire thing. We will go into the depth of filter sterilization in a separate session, which is planned sometime later in April. Okay. Sterilization by filtration is called as a cold method of sterilization, since it is the only method which does not rely either on elevated temperature or some other form of energy to destroy the microorganisms. Okay, so this is called as a cold method of sterilization. Actually, if you look at filter sterilization, it is wrong to say that it destroys a microorganism, because filtration does not destroy the microorganism. What filtration does is, genuinely the word filtration, it filters out the microbial life from the rest of the product. By choosing the right kind of a filter in the filter media, you are able to eliminate or retain the microbial life on one side of the filter, while the rest of the liquid along with the product passes on the other side. Therefore, you are separating the microbial life from the rest of the product and not actually killing those microorganisms. So the filters will then have to get disposed in the right manner or appropriate manner to get rid of that microbial life which you have filtered out. Okay, so please remember this, that filter sterilization, though it is used commonly that I'll filter sterilize a product, you are actually not killing the microorganism, you're just separating it out or filtering it out from the rest of the product. Okay. What are the different kind of filters used in our industry? Particle filters, micro filters, ultra filters, and nano filters. These are the four classification of filters which are used, and you will see a combination of all of these filters or some of these filters depending on the product being manufactured. Filters are then classified into hydrophilic filters and hydrophobic filters. So, as the name suggests, hydrophilic is something which wets spontaneously, hydrophobic is something which does not wet spontaneously. Hydrophilic filters are used to filter solutions and mainly aqueous solutions, while hydrophobic filters are used to filter gases or solvents or strongly acidic or alkaline solutions. So, when you look at the kind of filters you'll be using, if you are using in the sterile manufacturing an aqueous based product and you want to filter it, you would generally use a hydrophilic filter. If you were in the same process using air pressure or nitrogen pressure to drive the liquid from one equipment to the other or through the filter, then the air would be filtered through a hydrophobic filter. So you will again see hydrophobic filters, hydrophilic filters in your applications when you go inside the industry. The table below gives the different kind of filters, what kind of particles can it separate out, and what are the examples of what can get removed. So particle filters, as the name suggests, will remove particles, pollens, and some large bacteria between the range of 10 to 20 micro or 200 micrometers. Microfilters 0.1 to 10, most of the bacteria, yeast, and colloid get removed by using a microfilter. Ultrafilter is 0.001 to zero point 0.1. Most of the viruses and large organic compounds greater than 10,000 Daltons get removed by ultrafilter, and nanofilter is less than 0.001 micrometers, very, very small organic compounds and ions. Now, if you look at it, we talked about water used in the pharmaceutical industry, and we encountered there the use of ultrafilters and RO membranes and filtration techniques, and those are again used for particular contamination. So ultrafilter would be used in water, nanofilters would generally not be used. uh, but if you look at process, the sterile manufacturing process itself, when you are trying to remove viruses, especially in antibody manufacturing processes, then the type of cartridge or the type of filter unit which will be used to get rid of those viruses would be an ultrafilter. Okay, so with this, I'm going to stop this first part of the session because I want to spend the second session on sterilization decision tree. We're going to take some examples on that and see how those uh, decisions have to be taken when you are deciding what is the best method of sterilization, because we have various techniques. You could use moist heat, you could use dry heat, you could use filtration, you could use gas radiation, you could use chemical means. Now depending on uh, what material is has to be sterilized and what conditions it is in, you have to make a decision saying what is the best method of sterilization for me. And second session today, we are going to spend the time about 45 minutes discussing that decision making process. So I'm going to stop my presentation at this point in time, and I will open up the session for question and answers here, so that you can ask questions on the types of sterilization and be clear about it before we jump into the sterilization decision tree part of it. So students can please shoot questions on any of the sterilization techniques that we have talked about.
Sir, I have a question.
Yes.
Sir, tangential filters, what type of filters is used, sir?
Okay. So tangential flow filtration is a technique in which how you send the liquid into the filtration zone. Okay. Tangential flow filtration is nothing but a filter in which uh, the filter and the liquid are in the same vertical or a horizontal plane, meaning that you are sending the liquid parallel to the surface of the filter, and which is at a tangent, right? Because if you look at a filter and if you look at okay, just give me a second, I'll stop sharing my screen and bring out a figure which will help you understand this better. Okay. Can you see the screen, right? So this is a picture, a typical picture of how a tangential flow filtration works. So there is a membrane which is there. The product or the material to be filtered is moving in a space in between filters, and it is moving on the surface. Now these are arranged in a circular format generally, and when they are in a circular format, when you look at the product stream which is flowing next to the membrane, it is moving at a tangential in a tangential direction, and this tangential flow is also causing the filtration to occur. And this is, so this is a forced flow, which is you are pumping this flow here, and it is moving, and then it is going back in this loop here. And while doing so, the product or the either the product of interest or the waste is getting filtered out. So tangential flow filtration is a technique used for filtration. It is a methodology, just like you see a dead end filtration. So this is how the membranes will be permeate. So you saw RO membrane in water purification process. So you will send the liquid in the space which is the hole on the fiber here, and then when the feed goes out, the liquid or the permeate or the material which can get filtered out will flow out from the sides of the membrane, and the concentrated material passes through. So this is tangential for filtration. Now, where will you use it? You will use it in generally microfiltration and ultrafiltration or nanofiltration techniques, where you will use equipment which will have these modules of either in a rectangular format or in a hollow fiber membrane format or in spiral wound or in ceramic configurations, where the it is mounted in a housing, it is mounted in a tube. So imagine a tube in tube kind of a situation. So you will have one tube in which there will be a external tube which will be used for housing the internal tube. The internal tube is where your membrane is sitting, and the membrane has the hole or multiples of holes which are there. Again, let me see if I can get a picture of hollow fiber membrane for you. Uh, Okay, so this is a hollow fiber membrane which is there. So if you look at this part, there are multiple, like your spaghetti, which is there. There are multiple of those, noodles or straight line conduits, which are made out of materials like, for example, they are made out of Teflon. They could be made out of polyether sulfone or various other materials. So they are arranged in a circular pattern as a bundle. This is a typical hollow fiber membrane which is used. So there is a hollow fiber here. Now this is sealed at this point, at this junction here. The feed is sent here through this fiber, so they go inside the fibers, and on the other side of the fiber, the permeate comes out. So to collect all the permeate, you will have an external housing here, so that all the permeate gets collected and comes out through a particular nozzle itself. So this is, there should be some other pictures of a hollow fiber module. Uh, yeah, so this is how the module looks if you look at it. So this is like a housing. Inside the housing, you have the hollow fibers which are arranged, right? And there is a outer cover. So all the permeate gets collected on the outer cover and comes out through these two nozzles, while the feed is going through the central nozzle in and out. So this is what a tangential flow filtration is. A very interesting subject to again learn, widely used again for a lot of filtration applications in the industry, used in, for example, for purification processes, for a lot of industrial biotechnology based processes. So microfiltration, ultrafiltration, nanofiltration, all three of them would be where tangential flow filtration would occur. Even your RO membranes, which are used for water purification, use the principle of tangential flow filtration. Is that answer your question?
Yes, sir.
Right. Any other questions? Any questions on any of the types of sterilizations which are there? Please feel free to ask. Don't be shy, because these are things which you will have to apply when you get to the industry on one side, and on the other side also there are certain applications which you will have to be clear about as your own responsibility when you work in the industry. So, and knowing these principles, why we use a kind of technique, in what kind of situations do we use different techniques is important, because when we talk about the decision tree, sterilization decision tree, again this will become very, very important. So if there are any questions, please ask. uh, if there are no questions, then uh, we can probably take a break and come back in another 15 minutes, and then start our next session on sterilization decision tree. So, sir, if there are any no questions, I would suggest that we end the session here. Is everybody able to see my screen?
Yes, sir.
So, welcome back to this session. The decision tree for selection of the sterilization methods is the topic that we're going to cover. And there are a few important regulatory requirements which we need to just first talk about. So this is a excerpt from a quality manual, and I'm going to just read each of those, and then I'm going to explain that before we come to the decision tree making process. Those products intended to be sterile should be terminally sterilized in their final container, as clearly stated in the European Pharmacopoeia and in the CPMP notes for guidance. Where it is not possible to carry out terminal sterilization by heating due to formulation instability, a decision should be taken to utilize an alternative method of terminal sterilization, filtration, and or aseptic processing. It is recognized that new terminal sterilization processes other than those described in the pharmacopoeia may be available, right? And may also be developed to produce sterility assurance level equivalent to the present official methods which are there. And as such, and such processes, when properly validated, may offer alternative approaches. So let us just spend a few minutes on trying to understand what this statement is telling about. The most preferred methodology for ensuring that you do or produce a sterile product is a terminal sterilization process. Okay. What does that mean? What does that mean is that where a material can be subjected to a sterilization process in its final container, then the first thing we should do is we should definitely go ahead with a terminal sterilization process. Why is it so? Because it actually gives us a very short method of ensuring that the product which is in the final container is sterile. There is no human intervention after that particular position till it is administered to the patient, and therefore your product is safe to deliver to the patient. However, as we know, a lot of formulations today including a lot of biological compounds, cannot be terminally sterilized because they are not stable during sterilization by heat, and therefore a decision to use alternative method of terminal sterilization, filtration and or aseptic processing should be used. So again, if it is not terminally sterilizable by using heat as a technique, then first we should look at alternative methods of terminal sterilization, just like we studied on gamma radiation as one of the terminal sterilization philosophies, and then beta radiation, even ethylene oxide for that matter. That should be an alternative method. If that does not work, then we should see if filtration of the final product will help us as a process itself. And if not, uh, combined with the filtration, you have to do an aseptic processing. So aseptic processing is not the most preferred manufacturing process because it involves a lot of care and control at various stages of manufacturing. And therefore, terminal sterilization is the preferred method of manufacturing sterile products. So this is who is saying this? This is being said by CPMP, which is Committee for Proprietary Medicinal Products. And this is a paper which was presented by them in while talking about what should be the sterilization method choice or the decision tree. Okay. So this is the first very clear aspect, that when we are doing a sterilization decision, first preference should be, can we terminally sterilize the product? If that is not by heat, if that is not a choice, then are there any other terminal sterilization techniques? If not, then a filtration and an aseptic processing becomes your choice. Okay. Now, when moving down a decision tree, it is clear that these methods generally show decreasing levels of sterility assurance, and it is therefore essential for product quality and safety to ensure that the highest level of sterility assurance is achieved in conjugation with the lowest level of pre-sterilization bioburden appropriate. These decision trees are intended to assist in selection of the optimal sterilization method, taking into account the various complicating factors. Okay, so let's just understand this a little bit more. Why are they saying there is a decreased level of sterility assurance? When you have a product which is compounded or formulated in a vessel, and then it is directly filled into a vial or any primary packaging material, sealed, and then it is subject to terminal sterilization, you have the highest level of sterility assurance that although you have not followed certain uh, initial care while doing the formulation or whatever it is, your final product in its final container is absolutely sterile. So the assurance is 100% there, or is very high there. I wouldn't call it 100% there, but I would still call it as high. Now, when you do any other methodology like aseptic processing, then you are not going to be able to terminally sterilize the product. So you have now multiple factors at which you have to ensure that the sterility assurance is achieved. One could be in the compounding vessels itself, or if you do not use the compounding vessel as the, if you are using a filter to filter the solution into the holding tank before filtering, therefore using filter sterilization as one of the techniques, then the compounding vessels may not become so important as much as the final holding vessel becomes, because you have finished the formulation, you are then filtering it through a sterile filter into a tank, from where it is then fed to the filling machine, where it goes into the individual containers. So your filter, which is used for filtration, the holding tank, which is there, which is holding the bulk solution, and then the filling equipment where you have the vials as well as the entire filling mechanism, which could be either a rotary piston pump or a peristaltic pump, or with the tubing and the piping and the transfer piping between the filter to the holding vessel and holding vessel to the filling equipment. All of this need to be sterile because there are too many components involved. A failure in any one of those systems can compromise the sterility assurance levels. And that is the reason why the statement is made in CPMP saying that there is a decreased level of sterility assurance because now you have to deal with sterility assurance at multiple places rather than just one place, which was on the final container. So as a result, your chances or probability of having a sterility assurance breach is higher when you're talking about aseptic processing because you have multiple places which are there. Of course, today with the automation techniques, validation, more knowledge, we are able to achieve sterilization and sterility assurances in the aseptic processes also repeatedly and consistently. But there is always a factor where this any day a terminally sterilized product will give you a slightly better insurance on sterility assurance as compared to that of a aseptic process. There are other processes where you cannot filter the product, like if you were dealing with suspensions or dealing with emulsions, they may not be filterable. So in that situation, even your compounding vessels have to be now free of microbial contamination. So right from the first step of manufacturing till the last stage, you are not able to terminally sterilize the product, and therefore you have to make sure that at every step your sterility assurance is there. So the way you charge the compound, the way you dispense the products, the way you charge it into the compounding vessel, the vessel itself, the transfer pipings from there, the air which you pump into that vessel, everything has to be, subject to sterility assurances. And that is the reason why sterility assurance levels will be decreasing. I would rather want to use a word. This is an excerpt from CPMP, so I'm using the word as it is. But if I was to rewrite the statement, then I would write it as that the probability of a sterility assurance is the highest in terminally sterilized product, followed by aseptic processing, where you have a bulk filtration or a final filter sterilization possible just before filling. And the last would be where you can't have any filtration, like suspensions or emulsions, certain emulsions where you can't filter it, and therefore you have to make sure that right from the first step of manufacturing till it is filled and finished, you have to maintain sterility assurance. So your probability of a success on sterility assurance is the highest in terminally sterilized product as compared to the one where you don't do filtration. Okay. Now, the use of inappropriate heat labile packaging material cannot in itself be a sole reason for adoption of aseptic processing. Rather, manufacturers should choose the best sterilization method achievable for a given formulation and select the packaging material accordingly. However, it may be that choice of a packaging material for a given product, which has to be taken into account factors other than the method of sterilization, which may result in you having to need to use an aseptic process also. In such cases, these other factors need to be clearly documented, explained, and scientifically justified in a dossier. Conventionally, it has been accepted that the other factors, such as the type of container, route of administration, and patient benefit, have contributed to the choice of a particular container type which will not withstand terminal heat sterilization. For example, certain ophthalmic products, and such products are therefore manufactured by validated aseptic processing. In such cases, manufacturers have a duty to continue the search of acceptable alternative containers, which would allow the move to the preferred terminal sterilization in an acceptable time frame. Commercial consideration should not be used as a justification for not using terminal sterilization with the highest possible level of sterility assurance. So let's just decipher the statement a little bit more deeply. What the statement says is that just because you were using a container, the final formulation in a plastic container, which cannot be subjected to terminal sterilization, you cannot say because of that I am trying to use a aseptic process or trying to use a filtration based process. That is considered as an excuse because the first thing is that you have to make sure that the content inside the container, whether it's a solution or an injectable solution or a formulation which is going there, is first of all sterile, and then accordingly choose the right packaging material for it. So which is the right packaging material? Choose based on the fact that okay, I am able to terminally sterilize the formulation. It does not get affected. The property of the compound does not change if I subject it to terminal sterilization. And therefore, if I want to use terminal sterilization as a method, however, because I'm using now a plastic material, I don't want to switch to a aseptic condition. So let me find a container where I can terminally sterilize it. Okay, so this is the first statement which this guidance or which this paper is giving. All right. However, there are other factors which may be considered from a marketing authorization dossier, which may define what the packaging material should be. And what are these? You know, sometimes when you talk about ophthalmic containers, you cannot put a glass container there because it is always difficult to handle a glass bottle near the eye. What happens if the glass breaks and injures the eye? Whatever it is, a plastic bottle falls down from the hand, it does not break, and so on and so forth. So from that perspective, a lot of ophthalmic products come in plastic bottles. So in that situation, your choice is defined by the patient convenience and benefit and the route of administration, which is self-administered, which is there. A lot of times you use plastic syringes because of the kind of product which is filled there, which may be liable to certain factors which penetrate through glass. So from that perspective, when you are forced to choose a type of packaging material, then you will be allowed to use an aseptic process through validated processes and all that. However, in both these cases, just I'm sorry, I need to take a call. So just give me a second, please. Rishikesh ji. गुड मॉर्निंग ऋषिकेश जी, अगर आपको प्रॉब्लम नहीं है तो मैं एक आधे घंटे में फोन करूं? ठीक है, थैंक यू सो मच. Okay, right. Sorry for that. Okay, so now, but what does the guideline say? It says that even if you were forced to choose the aseptic process because of the container you choose, like in case of ophthalmic processes, it is the duty of the manufacturer to keep on searching for material so that you can move to terminal sterilization. So here, if you look at it, the preference by the pharmacopoeia and the CPMP notes for guidance is that where and possible you should use terminal sterilization. Where you are not using terminal sterilization, work towards a methodology, whether it's packaging, whether it's your process, to move it to terminal sterilization. Okay. Again, as I said, it is not possible to go there in every situation. If your product itself cannot withstand heat, then the question of terminal sterilization does not arise. So a lot of biologics product which you produce, which you are manufacturing today through monoclonal antibody formulations, a lot of other products which you are manufacturing in the industry, which are some of the complex injectables, for example, terminal sterilization is not an option because the formulation itself cannot withstand the heat. And in such situation, your only choice is aseptic processing. So when you are making a decision here, The decision is, if the product can withstand the terminal sterilization, then go all out and use that as a choice. However, if the product cannot withstand terminal sterilization and gets affected because of heat, then you please move towards moving your processes towards terminal sterilization, and don't choose aseptic as an option. So that's the first decision point, which is the guidance factor for all of us. Okay, so far clear? Is everybody clear on this? Because now we are just going to straight away get into two trees, and we are going to discuss that in detail. So if there are any questions on what I've just spoken, you can ask now, and then I will move to the decision tree. If something is not clear, please ask now. Okay, all clear. Good. So here is the first decision tree. Now we are talking about aqueous products. Okay, aqueous products meaning that the product is made using water is the main constituent. There may be additives, there may be salts, there may be certain other components, but it's primarily in aqueous base. So the first question which has to be asked when doing a selection of a sterilization method is, can the product be sterilized by moist heat at 121 degrees centigrade for 15 minutes? Okay. If the answer to that is yes, then use the sterilization technique, which is autoclaving, which is package it in a container and then push it into a autoclave or terminal sterilizer for doing your sterilization process. So this is the first question to ask. As I said, can I use moist heat to sterilize it at 121 degrees centigrade? If the answer is yes, go ahead and use only terminal sterilization. Now, the answer could be in 15 minutes, it does not get sterilized. Okay, with an FO value of greater than equal to 8 and achieving an sterility assurance of 10 to the power of minus 6, can you still achieve the sterilization? The answer could be yes or no. If the answer is yes, then again change the condition of moist heat sterilization and go ahead with the sterilization process. So here, if you look at it, the first thing is there is a first condition, which is the condition of 121 degrees centigrade at 15 minutes. Again, please remember 121 degrees centigrade is using saturated steam. This condition could be slightly different based on the product. So if I were to rewrite this statement again from a tree perspective, because this is again something which is defined by CPMP that we all follow. So 121 degrees centigrade for 15 minutes is using absolute saturated steam under zero air condition. Now there may be situations where you don't have 100% saturated steam, and in that situation the time may be slightly higher, so you could apply that. But the idea is that without changing the parameters of the sterilization and keeping it at the temperature around 121 degrees centigrade, and the minimum time, if you are able to achieve a sterilization, then use terminal sterilization as the process. If not, change the conditions of moist heat sterilization so that you achieve a sterility assurance level of 10 to the power of minus 6, where FO value is greater than equal to 8 minutes. Okay, so if the FO value is greater than equal to 8 minutes and you are achieving a sterility assurance level of 10 to the power of minus 6, by changing the condition of moist heat, if you are able to achieve the sterilization of the product, then use that as a technique. So again, that would be a technique whereby you will still use a terminal sterilization at a different condition. Okay. Now, the third is, okay, I can't achieve by doing this, I can't achieve by doing this. Then, can the product be filtered through a microbial retentive filter? Can you just filter it and get rid of the bioburden? If the answer is no, then your decision making changes. If the answer is yes, then by using a combination of filtration and aseptic processing, you could go ahead with the process. So if a filter can be used, so we talked about a lot of aqueous processes which are non-suspensions, non-emulsions, which could be filtered through a retentive filter. In that situation, you could do your formulation without worrying about sterility assurance of those vessels. You do the compounding, follow it with a microbial retentive filter, and because of this, you are able to achieve a liquid which is free of microbes. Hold it in a tank. So that tank and the associated piping for the filter housing, the filters, and from the holding tank to the filling machine needs to be subjected to aseptic process, which is nothing but sterilization in place and ensuring that it remains sterile. So you will combine the compound filter on one side of the filter. You will have a filter which is sterilized. You will pass the, or would be either pre-sterilized or sterilized, and will pass the liquid through it, as a result of which the liquid is free of microbes, and now you can directly go ahead and fill it as long as your equipment and components are sterile. So that is the technique. So this is a level of aseptic processing and aseptic filtration, but is not a full-fledged aseptic processing from start to finish. It is limited to a certain portion of your process itself. The last answer, no, I can't filter it through a microbial retentive filter. What are the situations here? Suspensions. I can't filter a suspension through a retentive filter, because if I do that, then the particles which are suspended in the formulation are critical for the injection themselves get filtered out, because they are larger than the microbe itself. So the microbial filter will keep the particles also apart from the microbial. So I can't filter it. In that situation, you have to use pre-sterilized individual components and aseptic compounding and filling, so that from the start till the end, every process step is, sterile or aseptic. What does this mean is that the way you charge your drug substance into the tank for compounding, the way you sterilize those compounding tanks, the way you transfer it from one tank to the other. If there were multiple tanks involved in a compounding process, then you would make solution one, solution two, and then you combine it into the third tank where you add the API and then send it out. Now, let me give you an example of how you can use various techniques. So let's say you were making a suspension, but the suspension is formed only when you combine two components together and add an API to it, right? In that situation, your individual component number one, which is a liquid, you could still filter, sterilize it, and transfer it to the tank. So your tank is sterilized or made bioburden free. You have a filter which is sterilized, and then you transfer this liquid from tank one to tank three. Same thing you do from tank 2 to tank 3, where two different systems or two different solutions are prepared, and they are filtered and then filled into tank 3, where suspension gets formed. And there you may have added an API in the tank 2, or you will directly add into tank 3. When you add that, and you are able to filter, sterilize it, because those solutions are filterable. They can be filtered without a problem, because you are still not in a suspension situation. And you enter into the third tank, and once you enter into the third tank, then there is no filtration possible. So right from that third tank onwards, till you fill it into the container, which is a vial or a cartridge or a PFS, you are not going to be able to use any filtration, and therefore everything has to be sterilized, autoclaved, in situ sterilized, autoclaved. Use single use components, use S2S connectors, whatever, but you have to maintain sterility assurance at each and every unit operation. So the difference of a terminal sterilization versus aseptic processes, that in aseptic processes at various unit operations, you have to ensure sterility assurances, whereas in terminal sterilization, your sterility assurance is only at the last stage. Okay. So this is the methodology for aqueous products. I'm now coming to how do you do if you had a non-aqueous solution, or if you had a solid or a dry powder. Okay. So if you had a known aqueous solution, semi-solid or dry powder, we have looked at the techniques of sterilization, and we know that the product cannot be sterilized using moist heat, right? So in that situation, what are you going to use? You're going to use dry heat. For using dry heat, you have to be able to sterilize it at 160 degrees centigrade for 120 minutes. That's the condition which is defined by CPMP. This condition could be slightly different, defined in different pharmacopoeias, or could be defined for a given situation. I would combine the first two steps of this decision making tree as a variant of each other, because you are still using dry heat as a sterilization technique. In one, you are defining a precondition of 160 degrees centigrade and 120 minutes. And in the other one, you are tweaking that cycle to still be able to do dry heat sterilization. So for me, this condition here and here, which is a decision-making tree, are one and the same, because ultimately you are ending up with a dry heat sterilization at a given condition to achieve a 10 to the power of -6 kill rate, right? So if the dry powder or the semi-solid or the non-aqueous liquid can be sterilized at 160 degrees centigrade for 120 minutes, then you will fill it in a container, you will subject it to dry heat, and you will send it out. If no, then you will change the combination of time and temperature so that you can achieve a sterility assurance level of 10 to the power of -6. And applying that combination of separate parameters of dry heat sterilization, you use a sterilization, dry heat sterilization as a methodology for treatment of the product. Now, both these conditions are the first choice of your sterilization decision. However, if it cannot be done because of the reason that no, you change the parameter, you are still not able to reasonably achieve 10 to the power of 6. It is not that you will not be able to reasonably achieve, but say the temperature goes very high or the time goes to like 7 hours, 8 hours, then it does not become a viable option at all. So in that situation, when you can't achieve this in a reasonable time and temperature, then your only choice is, can you sterilize it by a different method? And the different method, if you look at the decision tree, is talking about ionizing radiation with a absorbed minimum dose of greater than equal to 25 kilogray, right? Now, ionizing radiation is nothing but gamma radiation. So if you can sterilize the powder or the semi-solid or the non-aqueous liquid by an ionizing radiation, then use that as a technique so that you can fill the product and then do subject it to ionizing radiation. So ionizing radiation is an accepted methodology of sterilization by the pharmacopoeia, and that's why it sees its uh, reference here. Okay. Now, if the answer is yes, you go ahead and apply that as a technique, bypassing the dry heat as a option. But then, if the answer is no, then can you use it using a lower irradiation load? So if you look at it, the here the dose rate was defined as greater than equal to 25 kilogray, and in such a situation, if you said that at this dose rate it is affecting your product, or if it is causing an issue for you, that the product parameters are changing, the quality of the product is changing, then you can't use this as a technique. But the guidelines allows you to go ahead and choose a lower radiation dose but a validated method so that you can still use it. So again, these two are a variant of each other, that in this case, like you had a precondition which is defined and you could directly apply it. Because you could not apply it, you change the conditions and you still use dry heat. You are using an ionizing radiation in both these cases but you are having a variance, one at a defined level by the guidelines, which is greater than equal to 25 kilogram. In the other case, using a different condition or a lower dose, so that you could still use a terminal sterilization, which is a ionizing radiation. So you are using dry heat as the first choice. If not, then you are using ionizing radiation. Answer is no. Sorry, I can't use it. I have no ways in which I can use it. So, what are the conditions? Certain biological compounds, you can't heat sterilize them. You can't even radiation sterilize them, because the radiation will cause a effect on the biological substance itself, may cause this, right? In such situation, you can't expose it to radiations, and therefore, in both those cases, you are not able to use a technique of dry heat or radiation for sterilization. So, what is your choice? You come back to the choice that you made earlier. Can I filter the solution through a retentive filter? If the answer is yes, use aseptic filtration and aseptic processing techniques to filter the solution and generate your product which is there. Now you would say, but you said I cannot filter. Yeah, for powders you can't use it, semi-solid you can't use it, but for non-aqueous liquid this is an option. Because dry powders, sometimes what you could do in dry powders is that you could dissolve it in a liquid media which is filterable. You filter that media so that any microbial particles will get retained on the filter, while the powder which is dissolved in the liquid passes through. And then you precipitate out the powder after filtration using sterile techniques or aseptic processing techniques, and therefore you get a powder post that, which could be a combination of precipitation, so you remove the liquid and or you reverse precipitate it, or you change the phase, or you change the solvent, and as a result of which the powder gets the solid gets precipitated out. And then you have to do a filtration to remove the liquid and remove the solid and the liquid, and then take that solid and dry it out. Okay, so now you can imagine the number of steps which you are increasing just because you couldn't do this. You have to first dissolve the powder or the semi-solid into a liquid where it is freely soluble, then filter that, then reverse precipitate it by using different solvent. You don't have to filter it always. You could, even by using a different solvent, achieve the same situation. Like for example, a lot of times you use solvents like ethanol, you use solvents like IPA to dissolve the product, and by using that and filtering it off, you are able to just without filtration also sometimes able to achieve the required kill of the microbial component which may be present. Normally, after dissolution, you would still filter it so that any cell mass or anything can, kind of be removed before it is precipitated out, so that you don't have the toxins or the cell debris associated with the powder when you precipitate it out. Now, when you have then taken it into a solution, filtered it, you have filtered the solution, the powder is or the product of interest is still dissolved, you need to remove that product. So what do? You either would sometimes distill the solution if it was a solvent, and you would remove the excess solvent so that you change the concentration of the solubility of the powder to the liquid, and therefore it precipitates out, or it crystallizes out. You sometimes use a different phase. If you can't subject it to distillation, then you change the solvent, and therefore you make the liquid component in which the original powder was solubilized, more amenable to the next solvent, and therefore the solid precipitates out. There are various techniques of doing this. And then what do? The next thing you have to do is now you have to separate the liquid and the solid. Now that's a difficult one because yeah, when you have to do that, how do you do it in a sterile method? How do you do it in a closed condition? How do you make sure sterility assurance is achieved? You would generally end up using a centrifuge or some kind of a filtration device, which is a closed filtration device, collect the solid and then transfer it into a drying mechanism unless the equipment itself is capable of drying. So, for example, I don't know how many of you are aware about what is an agitated Nash filter, but an agitated Nash filter could be used. But to sterilize that agitated Nash filter is a task by itself. So if you look at the decision making tree, the reason why they preferences terminal sterilization is also because when you get into certain formulations and when you get into certain manufacturing of components, you will find that the number of unit operations may force you to have sterility assurance at different places, which is not always a easy task. And of course it is possible, you can have techniques to do it, but then it affects what? It affects the cost of the product, it affects the time taken to manufacture the product. And that is the reason why your preference is not to use this kind of techniques for the sterilization process. You would rather stick to something which can be terminally sterilized. Having said that, not all processes can be run through the terminal sterilization processes, and therefore you will have to go through this. So the industry has of course moved towards finding solutions for such challenges. Maybe 30 years back there was no filtration device which could be in situ sterilized and used like a standard filter, just like your Buckner funnels in the lab, where you just pour the liquid with the solid gets retained on the filter and the liquid goes out. So now you've got the solid, you have to dry it, you apply vacuum, load it into a VTD or a vacuum trade dryer or something like that, and you do it. Now, there are equipments which are available where you can filter the solution, remove the liquid, dry the powder within the same equipment without removing it, and then taking it out as a dry powder, which can be directly filled into vials in a sterile method. There are equipments available. One equipment, such equipment is manufactured by a company called Powder Systems Limited, for example. And that's called as a scalper or a refiner kind of an equipment. Is a variant of a filtration device where you could load a slurry into it, you could filter it, you could wash the powder, you could do whatever you wanted with the powder in terms of treating it or washing it out to remove all residual solvents, remove everything, and then dry it within that equipment all under sterile conditions, and then unload it in a sterile closed condition, and then directly take it for filling it on a filling machine. So that's one example of the equipment. There are other techniques of doing it. Sometimes you directly take a slurry and subject it to freeze drying in a sterile freeze dryer or a bulk freeze dryer, or even an active freeze dryer. These are other examples where you could do, once the freeze dried powder is ready, you just remove it. A lyophilized powder is ready, you remove it, and then you subject it to filling. So when you are especially dealing with powders, and there are a lot of products which are powders, especially a lot of your beta lactams and cephalosporins are all powder products. Also, there are certain complex injectables in terms of what are called as microspheres today, which are dry powders which are reconstituted before administering to the patient. And in all such situations you have powders, and either you have to use aseptic processes or you have to use the radiation methodology or heat. And generally in components like complex injectables, and I can talk about it because I've recently scaled up some of these products for a for one of our clients, and dry heat sterilization is not an option because the constituents of that product will melt away if you subject it to such temperatures. Ionizing radiation is also not an option there because of the fact that the chemistry of the product changes because of the kind of radiation that you use. So the only way to do it is to use a combination of aseptic processing and filtration techniques, where certain initial stages we filter, combine it into the stage where the powder gets precipitated or a microsphere gets formed, and then you have to subject it to filtration technique using one of the kinds of equipment that I spoke about, and then fill it as a powder into the final vial. So this is where I would like to kind of stop the discussion on sterilization decision making tree. We've spent about 45 minutes discussing this. Now I would like to see questions because this is a very, very important subject, because as pharmacologists who are employed in industry, or B Farm students who are working on compounding in R&D or formulation development, or are involved in tech transfers from while a new product is coming to you from either your own R&D or from an external resource, or you're working in a contract manufacturing where your client is giving you a product. It is important to understand the choice of sterilization technique, what decision making process went through, and why you are being asked to do a sterilization in a certain method. Because as a person who is manufacturing this compound, if you were also setting up your own facility, for example, it is your responsibility to give a sterility assurance. And when you have to give a sterility assurance, you have to be sure that you will be able to achieve consistently and repeatedly the sterility assurance levels that are demanded out of that product. And that, trust me, is not impossible, not very difficult if there are systems, procedures, validations which are done, automation techniques which are applied, and people who are trained. So already I brought in 4 variables for you there. And in such situations, your uh, probability of failure on sterility assurance increases. Once a failure occurs on any sterility assurance, it leads to an investigation where you can't manufacture that product till you have investigated the root cause of why the sterility failed, and have put in mechanisms, techniques, procedures, necessary controls to make sure that this will not recur. So when a sterility fails in of a batch fails in a sterile manufacturing process, I'm sure the lectures on quality systems given by Lakshmi Madam and other faculty members on this training course have spoken a lot about investigations, have talked about what happens when a batch fails. But I can tell you that when a batch fails, for sure, to pinpoint the root cause becomes an extremely difficult task, and also becomes a time consuming process. We've seen real lifetime situations where we had a failure of a sterility assurance, and for us to get back to normalcy took 45 days. For a sterile manufacturing facility, or for a facility manufacturing sterile products, 45 days of production shutdown means a lot of commercial loss. And that is why it is important that whatever processes that we follow inside the manufacturing suite is completely understood, is secured, is validated, especially from a sterility assurance level perspective, because you are playing with lives of people. If you don't assure sterility, you are administering, or you're manufacturing a product which is going to a patient who will take it, and that patient could have a negative effect of it, which can cause life-threatening issues. People can lose lives. It can bring shutdown of the manufacturing facility where it was produced, or a bad reputation and a huge commercial loss. So therefore, it is very, very important that sterility assurances on uh, drug products is an absolute chapter, an absolute subject of prime importance, not only from a perspective of the processes and the equipments, but also the procedures and training of the manpower, because ultimately your processes are are slightly dependent on the manpower which is used. Even if you have a completely automated system, there is at least a few manual steps or manual interventions or manual involvement of manpower in that process. By adapting automation, yes, you can reduce a lot of those errors, but you can't definitely avoid failures, because even in an automated process, if one temperature probe fails and it goes undetected, you could be having a wrong temperature sensor giving you a wrong reading, that instead of 121 the temperature was actually 110, but it had an error, calibration error, or somebody forgot to calibrate it and it showed 120 degrees centigrade, and as a result you had a sterility failure. Now, to go and investigate that it failed because of that one temperature probe which was sitting in one drain line just before the sterility battery limit or the sterile battery limit was ending, is a difficult task. And for anybody working in a facility, it becomes very, very important to pay full attention to ensure that sterility assurance is never ever compromised. Okay, so with this few words on the caution, after talking about the sterilization decision tree, I now open the session for question and answers, and students are free to ask questions and answers on the sterility decision tree. Also can ask questions on the types of sterilization if something has come up after the last set of questions. So go ahead.
Sir, I have one question.
Yes, please.
What is pulse humidification?
Okay, that was in ethylene oxide.
Yeah.
Okay, so just give me a second. I'll just go to the. Okay. So what you're doing is, in a chamber, just like in your autoclave or a steam sterilizer, you are removing the air first, right? Now, when you remove the air and you are humidifying the chamber, because you have to create the right amount of humidity inside the chamber using ethylene oxide. Okay, so ethylene oxide and carbon dioxide will be mixed together and they will be introduced into the chamber, right? To achieve have to have a right humidity of 35 to 80%. So when you are removing the air from the chamber and humidifying the chamber so that you achieve 35 to 80% humidity inside it, it may not be a constant value. Why is it not a constant value? Because for a presence of a humidity, what do you need? You need an air. But now you remove the air partially, and there is some amount of air and moisture which is present inside the chamber. There are situations where that humidity will fall, will not be a constant there. So what will you do is that you will humidify it by sending in sprays of moisture. You will probably bring the humidity to say 40 54% or 55%, which is the target humidity in this case. And after you've brought it to 55%, you hold it for a very small section, and you will then see that the humidity is fluctuating. So you again introduce a spray of water so that it goes back to 55% or slightly above 55%. So that is the technique which is used here in this phase where you achieve the humidity. You will see a variance by seeing that you will humidify it, and then you will see a drop, you will rehumidify it, and you will see a drop, you will rehumidify it and see a drop, and you will try and get there to a stage where now you are ready to introduce the ethylene oxide and carbon dioxide. When you introduce ethylene oxide and carbon dioxide itself, also you will see that the water molecules are formed, because ethylene oxide disintegrates into water very easily when it is in a gaseous form and comes in contact with any material. So in that situation, your humidity levels will start to fluctuate. So what you have to do is you have to maintain that 55 degree, 55%, 35 to 80. So you're maintaining about 54% RH. To maintain that, you need to sometimes introduce more water into the system so that you are maintaining the humidity at a particular level. So it's a technique by which you are controlling the humidity during the process of sterilization, but trying to keep it constant before your gas admission, so that you are not going to be lower than the set value of 35% RH or whatever your validated value is. Clear? So pulsed humidification is achieved by introducing shots of moisture or a spray of water introduced, just like sometimes when you have these uh, large halls in which there are those perfumes kept, right? And you see suddenly a pulse of that perfume is just sprayed into the room, right? To diffuse it. Similarly, here you will pulse the moisture into the chamber so that there is a increase in the moisture level before it drops down, because there is a possibility that the moisture level will fall because of its interaction with the environment inside the chamber. Could be with the material, could be because of the chamber material itself. So to maintain that, you just do a pulse humidification. Does that answer your question?
Okay, sir.
All right. Any other questions? No questions? I just want to. So, has everybody understood the decision making process? Very, very important. I am not seeing any questions here, which either I have managed to explain you properly, or don't be afraid to ask questions, please, because this is very, very important topic. uh, don't think about how small or big the question is. It does not matter. Question is a question. You have to have that clarity in your own minds and not look around whether asking that question will draw any uh, question mark from other colleagues of yours who are sitting in the room. Please don't be afraid to ask questions, because this is a very, very important topic that we are discussing.
Sir, I have another question.
Yes.
In the aqueous product, sir, F0 value is greater than 8 minutes to achieve the sterility assurance level of less than 10 to the power of -6. I did not understand this.
Okay, so F0 is what? F0, we have again, you have the definitions of the F0, which is here. F0 of a saturated steam sterilization process. Now, F is a value where you are looking at the change of the D value, okay, which is the time in minutes of exposure at a given temperature that causes 1 log reduction in the specific microorganism. F0 is the value of the saturated steam process where lethality is expressed in terms of equivalent time in minutes at a temperature of 121 degrees centigrade. So D value is saying at a given temperature, whatever the temperature, if I'm able to achieve 1 log reduction, that is my D value. Okay. F0 saying 121 is constant. What is the time that I will take to have a lethality rate that I'm looking at? So if your F0 value is, so F0 is expressed as at a particular temperature, F0 is expressed as a time, right?
Yes.
So if the time is greater than 8 minutes, right? So let's go to that sheet. Yes, time of F0 is 8 minutes, and your SL stability assurance achieved is less than equal to 10 to the power of minus 6. If your F0 is greater than 8 minutes, by changing the conditions, you will still be able to achieve the sterilization by terminal sterilization technique. So you have to, we will have a session on F0 tomorrow. In that, we will do some examples of how F0 value, D value, sterility assurance values are arrived at. In that, you will apply this formula to say that when my F0 value is greater than equal to 8 minutes, which means I need a time of more than 8 minutes to achieve an SL of less than 10 to the power of minus 6, then I will still be able to, by changing the condition, be able to apply the terminal sterilization technique, right? So that is what you have
Yes.
to apply here. So as I said, the condition at which you are doing terminal sterilization is what you are playing around with. These values are something which are given as by CPMP. As I said, 121 for 15 minutes is something given in the guideline. Whether, but this is on what condition? At saturated steam at 121 degrees centigrade at absolute pressure of 1.2 bar for 15 minutes, you will achieve sterilization. But we know that we will not have saturated steam. We know that we may have a pressure fluctuation. So those conditions need to be varied. How do you vary those conditions and how do you validate those conditions? You will use F0 value and sterility assurance levels to say and validate whether by changing those conditions you are within this condition. So the condition which they are putting is that for us to have a reasonable kill rate, if your F0 value is greater than equal to 8 minutes and is achieving an SL of less than 10 to the power of minus 6 within those that 8 minutes, then you can still, by changing the condition, be able to achieve your moist hit as a sterilization technique, as terminal sterilization technique. Clear?
Yes, sir.
Okay. All right. Any other questions? No questions? Okay. So then we will take a break for another 10 minutes now, not 15 minutes. We will come back at 11:30 and we will take up the next topic, which is types of autoclaves. Okay. Is everybody back?
Yes, sir, they're coming.
Okay. Just let me know once everybody is in so I can then start the session.
Okay, sir.
Sir, everyone is here. We can start.
Okay, thank you. So, okay, this session, actually, a lot of it was earlier covered in the moist heat sterilizers, but we are going to revisit some of those principles, and then we will move to the types of autoclaves. This lecture is spread over 2 sessions. So I'm going to cover 50% of the discussion in this session, and then move over to the types of autoclaves mostly in the next session. In this session, I'm going to just review and revisit some of the topics that we have learned and give you a sneak peek into the type of autoclaves. Okay, so let me just get rid of, wait, this one. What's happening? All right, everybody is able to see my screen, I guess. All right, so some of these pictures you have seen in the past. I'm just bringing in these pictures again from the previous session just to rekindle your memories that we had looked at some of these autoclaves which are there. This was the double door autoclave, a large one in industrial setup. This is showing the internals of the same autoclave with third trolley. This is a smaller version of a laboratory autoclave, a different size. But I brought in a new picture of this autoclave, which is a laboratory scale autoclave, which is also used in a lot of applications. And these kind of autoclaves in laboratory are used in hospitals, are used in microbiology labs, are used in smaller applications where the quantum of your autoclaving material is smaller. So depending on the volume of material that you use, you decide the kind of autoclave and the type of autoclave that you need. And we will talk more about it as we grow across. Of course, we are focusing on the moist heat steam sterilization when we talk about autoclaving, because that's where it is referred. So I'm going to give you a little bit of a history of autoclaving. So Napoleon Bonaparte, when he was fighting a war and trying to conquer the world, on a particular day, his entire army fell sick, and that was because of a contamination in the food. Then, somewhere in the 1880s, there was a French microbiologist who actually said that I will find a technique for you by which I can make the food less harmful. I don't think it was 1880, it was probably much earlier than that. And that's where the technique of autoclaving was kind of invented. So autoclaves are also known as steam sterilizers. They are typically used for healthcare or industrial applications. Now, why do we just say industrial applications? Because autoclaves are also used in a lot of food manufacturing industry applications, right? So all the food that we talk about, the ready to eat stuff which we get today, is all subjected to steam sterilization before it is assembled together and then packaged out, right? So that's why autoclaving is an important technique which is used not only in the healthcare industry but in industrial application. It is also used a lot in hospitals for healthcare, so it covers under healthcare. But the autoclaves which are used in the hospitals are slightly of a different type as compared to what you use in the industry. Ultimately, autoclave is nothing but a steam sterilizer. It is equipment that uses steam under pressure to kill harmful bacteria, microorganisms, fungi, spores, which are placed inside the pressure vessel. The items are heated to an appropriate sterilization temperature for a given amount of time. The moisture in the steam efficiently transfers heat to the items to destroy the protein structure of the bacteria and the spores. Principle remains the same. Even the pressure cooker at our homes is an autoclave, is a steam sterilizer, because what do? We put in the food items into that, we have water into it, we create a steam pressure, and we leave it there under steam pressure for a certain amount of time. By doing so, we are actually sterilizing the product which is inside that. The reason why idli is considered to be one of the most healthiest breakfast in the world is because of the fact that it is a steam sterilized breakfast, right? And therefore, it is pretty safe from a microbial contamination perspective. So autoclave is a technique which is used, or steam sterilization is a technique which is used in multiple places. Of course, the kind of machines that are used for food manufacturing are completely different than those used in sterile manufacturing. But the invention of the autoclave actually, and interestingly, happened from a food requirement and not from a medical requirement. Okay, so autoclave is in healthcare, which is what is the subject of our interest, is typically used as a nomenclature to describe a steam sterilizer. So autoclave, when we say autoclave, it always refers to a steam sterilization, which is moist heat sterilization technique. ANSI and AMI, which is American Institutes of Pressure Regulation and Standards for Manufacturing of Equipment, provides the guideline for processing of autoclaves, which are manufactured for these purposes, for medical devices also. So there are guidelines which are there, and we are going to talk in the lecture tomorrow about EN 285, which is the Bible or the standard which is used for autoclave design and validation. So we are going to spend some time on it, because as such this topic is partly discussed earlier, so I don't want to come back with the same slides or same discussion points when we are coming to it. Just a trivia, that steam digester, a prototype of the autoclave that is better known as a pressure cooker, was invented by a French-born physicist called Denis Papin in 1679. However, it was not until 1879 that a French microbiologist called Charles Chamberlain created a new version called the autoclave to be used in the medical application. So the what was invented, or what was manufactured by the French microbiologist Charles Chamberlain is actually what we use today. It's a vessel which is tightened, has got a lid, close it. Of course, it is secured for pressure. You put in water and you autoclave it. So very much the concept remains the same. The configurations have changed, etc. The science of disinfection and sterilization began in 1881 with the research of Robert Koch on disinfecting properties of steam and hot air. So while the steam digester or the pressure cooker, which was used in the food industry, was available since 1679, and then subsequently used by the microbiologist Charles Chamberlain in its current form of pressure cooker. The disinfection properties of steam was what was discovered by a scientist called Robert Koch in 1881. And he demonstrated that the greater power of penetration existed by moist heat compared to that of dry heat, because dry heat is not as penetrating as a moist heat. The presence of moisture allows the cell walls to be dilated, and therefore the penetration is very fast. So it was in 1881 that Robert Koch demonstrated the disinfection properties and therefore the sterilization properties subsequently. So finally, in 1933, the modern autoclave technology was introduced as a first pressure steam sterilization that controlled performance by measuring the temperature in the chamber drain line. Prior to this date, the pressure was sole indication of the control with no means to verify the temperature or air elimination. So we have discussed this in the past that removal of air is important, temperature is important, pressure is important. So all the earlier techniques, and even in your residence, when you use a pressure cooker, you don't go ahead and measure the temperature, right? You're just measuring the pressure there. There's a pressure, the pressure cooker is built for a certain pressure. When the pressure is reached, it releases the pressure. You allow it for a certain time, and then your sterilization is done. But that combining it as a technique for sterilization, effective sterilization, using the temperature of the chamber in its drain line, and time, and ensuring that the air is eliminated, was only in 1933 that it got kind of established. So if you look at the timelines, it was more than 50 years that it took to arrive at the conditions which were critical for an autoclave to work. Over time, new autoclave technologies have been developed, of course, including pre-vacuum cycles in 1958 and steam flush pressure pulse in 1987, allowing the science to evolve into autoclaves or steam sterilizers, which are used in hospitals and industry today. So when we look at it, a lot of work, if you start from 1879 till 1958, has been done to arrive at the modern techniques which are used. Even when we use a pressure cooker at home, we allow the steam to come out as a continuous stream. Before that, whistle is put on top of the pressure cooker, so that we are eliminating air. All this is a technique which has come from a science that if you want an effective sterilization, air has to be eliminated. So this is an interesting history, which I also discovered while preparing the slides on type of autoclaves, and therefore I thought it was interesting to bring it to the class. It's not going to be something that you're going to be quizzed upon or asked questions on, even in the industry, but it is interesting to know how this development happened. The working principle of autoclave, used in healthcare setting to sterilize medical devices, is used in for component preparation in the industry. The sterilized items are placed inside the pressure vessel. The time, temperature, and steam quality are the three important factors which contribute to it. Of course, we are going to talk about all the factors which affect autoclave in the subsequent slides, but I'm going to quickly rush them through because we have already been through that. So the three broad principles under which an autoclave operates is the conditioning phase, where you remove the air either by using a vacuum as a means, or by allowing the steam to displace the air. Okay. So as we said, in dynamic type of steam sterilizers, you remove the air from the chamber using vacuum system, or it can be just removed by giving a series of steam flushes and pressure pulses. So you introduce steam into the chamber, allow it to dwell there for a certain time and push the air out, and then keep on doing a pressure and steam pressurize the chamber using steam flushes so that the air gets displaced. Why will the air get displaced? Because the air which is cold will try to escape out from the top or from the easiest path possible, while the steam will dwell into the system. Right. So air removal is very, very important, and generally in the modern equipment you will see that vacuum is used for removal of the air. So conditioning phase is the first phase. Exposure phase, of course, where you admit the steam continuously into the chamber, increasing the pressure and the temperature inside the at a predetermined level. The cycle enters into the exposure phase, where the items are held at a sterilization temperature for fixed amount of time required to sterilize them. So this is the time when you initially do the air removal, followed by heating it to the temperature of 121 or 123 plus or minus 2 degrees centigrade at a pressure of 1.2 when we refer to saturated steam, or an equivalent of that saturated steam, the pressure and temperature condition, and therefore you expose the items to that for a prefixed time. And then you have to get rid of that steam, so you allow the sterilizer to drain by opening the steam. You can also you also allow the items to dry. Now in the autoclaves which are there available today, you do this by drawing the vacuum from the system to remove the steam, and simultaneously introducing sterile air so that you can dry the loads much faster. If you allow them to dry naturally, it will take a lot of time. In a real-time manufacturing operation, you have to carry out maybe about 5 or 6 cycles, or sometimes even 7 cycles to 8 cycles in a day, in a given number of shifts. So in that situation, if you have to wait for the chamber to cool down and to dry, it will take a long time if you allow it to happen naturally. So you have to use mechanical means of vacuum and air injection into the system to be able to dry the items, and also to be able to remove the steam and cool the area, because you can't remove an item when it is hot. You cannot open a pressure cooker when or autoclave when it is in hot condition, because the steam can burn people, right, who are around that autoclave. So it is very important to have the conditioning phase and exposure phase to achieve the right sterilization, and exhaust to cool down the content, so that, and to dry the load so that you can remove them and start using them. In the industry, you are going to use mechanical means to run the exhaust phase. Quality of steam is vital to the success. So we have seen that it has to be saturated. In true definitions, 97% steam, 3% moisture is a recommended ratio for heat transfer. When steam moisture content is less than 3%, it is normally referred to as superheated steam. But in generally industry terms, you might have a ratio of moisture slightly higher than 3%. In such situation, you need to look at the steam tables and increase the temperature, or to change the conditions at which you do sterilization, so that you achieve the effective kill rate of 10 to the power of -6. The commonly recommended temperature are, of course, 121, 132, 135. Generally, you choose 121, but that's a saturated steam, and depending on the type of material that you are trying to do, you have to choose the temperatures of the steam accordingly. Generally, the most widely used in the industry is 121, or slightly higher than 121, 123 plus or minus 2, as I said, because remember that in any manufacturing environment, you are not going to have the temperature stay fixed at that 120. Why is that? Because once you enter the hold time, right, there will be a dynamic situation inside the autoclave where some amount of condensation occurs. So the temperature tends to drop, or the pressure tends to drop. In such a situation, you need to inject steam in pulses into the autoclave during the hold time itself, so that it maintains that 121 degrees centigrade. And therefore, you always define a range at which you are going to do the autoclaving, and not of a single item. So if 121 was the temperature at which your FO values were established, then you centigrade. So at no given condition, my temperature goes below 121, and it is not also overheated, so that I end up into too much of an overkill, or burn out the products. So you will always define a temperature range at which you are doing autoclaving. and a pressure range at which you are doing autoclaving. So you generally, as I said, you heard me say 123 plus or minus 2, pressure range 1.3 plus or minus 0.1. So that's how you keep it. It's not, please don't use those figures for any of your applications. It is an established parameter which is validated and then it is arrived at. So you would see that in your batch manufacturing records, or you would see that in the data in the microbiology autoclave. So you always set it up, because no equipment can maintain one constant value. There is always a tolerance. Okay, we've seen this. These are the different phases. So there is a pre-vacuum, then vacuuming, then you're heating up, then you're holding it, then you're venting it out, then you're vacuum drying it. So I'm not going to dwell too much on this. Factors which are critical for the assurance of successful steam sterilization. I'm revisiting this topic because of the fact that we need to be clear that time is a very, very important factor, or these 6 factors which I'm going to talk about are critical factors for assurance of a steam sterilization cycle. So time of exposure, the time at which you expose the load inside the autoclave. So whatever you put inside the autoclave to sterilize in one go is referred to as a load. And when you are validating an autoclave, we are going to talk about autoclave cycle development and autoclave cycle validation in one of the sessions. I think it's the next session on the 10th of April. During that time, we will arrive at how do we define load patterns, how do we make sure that the loads are put inside the autoclave so that you achieve a proper sterilization. So the time of exposure becomes very, very important, that for a given load, you have sufficient time so that you have a complete kill, or a kill rate of 10 to the power of minus 6, what we need to achieve. So what do you use? You use Geobacillus stereothermophilus spores. So there are pre-spiked strips of Geobacillus stereothermophilus which you keep inside the autoclave along with the load at various places. You subject the load to the steam sterilization, and then you take out these strips of Geobacillus stereothermophilus. You know how many strips, how many spores were there before you put them in, and then after the sterilization cycle you test them to make sure that none of them are surviving, because those strips are chosen so that you have a 10 to the power of 6 kill rate or higher. So that's a technique which is used for measuring the success of steam sterilization. When you do a cycle development, actually, you will use more of this. When you do the actual steam sterilization on a regular basis, you do use biological indicators, but you will decide the worst case location, or a few cold spots as they are called, and only place the biological indicators there during every manufacturing batch. Sometimes people don't put it during manufacturing batch and go by the control system, because they have robust control systems and therefore there is no need to put too many steps. But generally microbiologists will insist that at least a few steps are put even with a regular manufacturing cycle, because those are the ones that they will go and plate. You of course will do a bovidic test, which we spoke about in the earlier session of moist heat sterilization, so that you are sure that there is proper air removal and penetration of the steam. So both these combined together, the biological indicators and the Bovie test, is what is used to make sure that your autoclave is correctly working batch after batch, cycle after cycle. Okay. The D value we have already visited. For Geobacillus, it is between 1.5 to 3 minutes at 121 degrees centigrade, which allows you to give a log reduction by 1 log, which is 90% kill rate at 121 degrees centigrade. That timeline is 3 minutes for Geobacillus stereothermophilus. So time is a very important factor. Temperature is another critical factor because the temperature defines at what temperature you're going to achieve sterilization. Again, we have spoken about this in the past. What is the relationship between temperature, pressure, and therefore time? And I'm not going to again dwell on it. So you see 121 degrees centigrade, 12 minutes. So if you look at the sterility assurance decision tree making process, sterilization decision tree making process, you saw a figure of 15 minutes. So 12 minutes is what is a validated time. So you take a slight overage and say, okay, 15 minutes, 121 degrees centigrade, I'll be able to do moist sterilization. But this is not a, this is true for a given load. When you have a different load, you have this cycle has to be validated. So it could be 30 minutes, it could be 20 minutes, it could be 40 minutes. It depends on the kind of load that you put inside the autoclave. So time is important, temperature is important, moisture is important, because moisture is the one which is able to penetrate into the cell wall, coagulate the proteins and denature them. So given that moisture is very, very important as a factor, if you do not use moist heat or steam, if you use supersaturated steam, you are going to create into okay, you're going to create contamination within the system, which is not recommended, which is not something that you want to look. So you want to use saturated steam and not super saturated steam into the steam sterilization process. So moisture is important important factor. Direct contact, it is important that the steam touches the object which has to be sterilized. So it is very important that you expose it properly. So that is important. Air removal, we have spoken enough about it in the preconditioning, and therefore air removal is the being the biggest deterrent. We have to make sure it is removed. Drying, when you unload the items from the autoclave after the steam sterilization, you don't then want them dripping. So you need to make sure, because the steam has come into contact, it is condensed on the material, you want to dry that fluid before you use it. So a drying cycle becomes important. So you use vacuum and air as a combination. Now, why am I bringing these factors again? Because you will say, we've already studied this. Why? Because when we are discussing the type of autoclaves, it is important to consider how each one of these factors are going to be achieved in those different type of autoclaves, and therefore what is the most efficient way of doing autoclave. And there is no right or wrong. It is always, you will do an autoclaving based on the application which is there, and based on the configurations which are there, what best suits your load. Again, sterilization decision process becomes applicable here also, because when you are doing a sterilization using moist heat, what is the ideal load that you will put inside the autoclave? What is the kind of load that you want can help you determine the type of autoclave that you want to. You're clear. I want to use moist heat steam sterilization. Now, what autoclave to buy is based on the process that you're following in autoclaving. So when I come to the type of autoclaves, and this is going to be my last slide for today's lecture, because I'm going to spend more time explaining each type of these autoclave in the next session. But I'll give you a sneak peek into a different type of autoclaves. Now, when you go and to any of the industrial sectors, including hospitals, including industry, you will see these kind of configurations of the autoclaves, apart from the one which we saw. So this was the autoclave which I had shown in the first slide, which was a nice looking one. And this is something which is a large automatic hospital autoclave. It is called as, or it could be also used in your laboratories in the microbiology, where you load from one side, unload it from the other side, or you could load it from the same side and unload it from the same side also. So this is when you have a lot of load and lot of cycles to do, you try and use a large autoclave so that your number of cycles or the autoclaving is achieved for a large number of materials within a short span. Okay. So you have these smaller ones, pressure cooker type, in small clinics, in small medical centers, or even in laboratories. When you are trying to deal with very small quantum of components, you can use a pressure cooker type autoclave. Water is filled, components are placed inside it, it is sealed. There are normally these knobs which you tighten with a tool, hand tool. It has got a pressure gauge, it has got a safety valve, very similar in construction to our pressure cooker at home, but it's a slightly different construction because it has to meet certain criteria of pressure vessel, unlike in the homes where it is a lot more safer. It's generally electrically heated, so you place the water, there'll be a electrical heater coil, just like what we use, similar to what we use in the residences for heating water in buckets. But of course, it has got a sleeve in which it is kept. The water is filled inside the chamber, sufficient quantity not to wet the entire material. Material is placed inside a small kind of a stand, and then you subject it to heating. So it works on the principle, but here there is a measurement of pressure or temperature, but you're not really having a true control here, because there is no active feedback from the temperature gauge to the heater. It is heated, and it purely depends on the pressure safety devices which are there. So it's a pressure cooker type. That's why it's called as a pressure cooker type. Then you have the laboratory autoclaves, which are small ones. These are used in normally again in clinics and again in hospitals for autoclaving components. So your surgical instruments, your instruments used by doctors are generally done using this. Again, this has a a small water tank at the bottom where water is there. This is sealed. When you seal it and lock it, it becomes like a pressure chamber, which is horizontal. In nature, you have a control system where you feed the temperature and the time, and it takes a full control of the system, autoclaves it, and just like a microwave oven at the home has a timer, goes off and gives you a thing. Again, this can be clubbed with a vacuum pump for a proper drying, but generally for a pressure cooker type and a laboratory autoclave type, the material will probably come out much more wetter as compared to the large autoclaves which you use. But this can, of course, be clubbed with a vacuum pump to dry the loads. So no issues about it. We can achieve the drying. Then there are vertical autoclaves. These are normally in the range of less than 10 liters, right? Up to 10 liters, because they are normally portable. You can keep them on a laboratory bench and operate them. Then you have these vertical autoclaves. These are in the range of about 40, 100 liters, 200 liters, 300 liters. They are very similar to the pressure cooker design, but in this case, what is generally there is that there is an inner chamber and an outer chamber. Outer chamber is where the water gets filled up. The inner chamber is where you keep the loads, and then you again heat it electrically. You also have certain vertical autoclaves where you can introduce steam directly and not be dependent on the water evaporation there. The level of the water. So generally, if it's a water filled one, then you will have a level indicator of the water to make sure that the water level does not dip. It's again tightened using wing nuts. On the top, there is a temperature probe, and there is again the pressure safety devices. In this case, you could, of course, have controls where you link the temperature probe to the heater so that the heater cuts off when the temperature is reached, and therefore you don't go into an overheat mode. However, the pressure cannot be controlled. In this case, you don't, again, vacuumizing vertical autoclaves of this design are difficult. Of course, there are modern vertical autoclaves. This is also a picture of a vertical autoclave. This is by one of the companies called Fedigari. They have vertical autoclaves which are meant for laboratory purposes and will have can be combined with vacuum for drying the loads. But again, principally it is vertical. So it's a configuration which is telling you that the autoclave is vertical or horizontal. Horizontal is that the chamber is horizontal in nature. So this is horizontal, this is horizontal, this is horizontal. These are vertical chambers. Okay, even this is horizontal for that. Okay. Then you have the horizontal autoclave. You see a circular chamber here. So in the older days, the circular chamber was found to be the most effective from a heat transfer perspective, and therefore it was used. However, when you look at horizontal autoclave or any circular autoclave, the effective load utilization is lower, because when you have a circle, the portions at which the circle is smaller than the diameter or a certain tangent or an arc, sorry, you cannot load the material inside it. So as a result, there is a huge amount of space which is left empty, and therefore the effective loading, so effective amount of load which goes inside the circular chamber is limited when it is horizontal in nature. So that's like, having trying to load a tray in a circular thing, you can only load it of a certain dimension. But this was preferred because there were no sharp corners, there were no 90-degree edges, and as a result of which the steam distribution was much more better. Till people and engineers came out with design of rectangular chambers, which is what you see here and here, where rectangular chambers, you had the position where you didn't need to make it completely circular. You could afford to keep the top and the bottom as flats, the sides as vertical, so you had a proper flow of steam any which ways. And then the junctions were made rounded or with a slight curve, so that you didn't have 90-degree angles where you could have the particulate contamination and therefore a microbial contamination lodging out, and it was self-cleaning, in the sense that if something got stuck here, it would anyway slide down because there was a rounded edge here. So it's like a rounded edge on a rectangle at the top, which is what you see here also. You see that there's a rounded edge here. So if you had a rounded edge inside the chamber also, you would not have the fear of any contamination getting stuck there. So rectangular chambers were used. Now the efficiency of loading on a rectangular chamber is much better. And therefore you could make large chambers. You could make large chambers, you could autoclave larger loads, and therefore when you had very large continuous manufacturing plants or plants which are running, producing a lot of injectable products, then rectangular chambers, of course, become a preferred choice. Even in a microbiology lab, a rectangular chamber is today preferred because of the fact that it can handle larger loads. And in a microbiology lab, when you're running too many tests, you need large autoclaved material or components, and therefore horizontal chambers are used. I'm not saying circular chambers are not used. The industry uses circular chambers as well as horizontal chambers, but these are just configurations in terms of geometry. What I've told you is only the geometrical types of autoclaves which are there: vertical, horizontal, rectangular, circular. Okay, but this is not the only technique by which autoclaves are classified. I'm going to cover those tomorrow morning, first session, where I'm going to tell you what are the types of autoclaves when classified in the industry. And that is the first and the most important criteria of classification of autoclaves. And of course, the geometry is the second part of it. The third type of autoclaves are based on applications. And I will touch upon all these three in more depth in the session tomorrow. I'm going to now leave a session open for question and answer as an introduction to autoclaves. If you have questions on any of the principles of autoclaves or the phases of autoclave, please ask questions. Again, I know we have done this session in the past. These slides you have seen in the past, but if there are any questions which are in your mind, please ask them before we deep dive into the types of autoclaves tomorrow and the EN 285 regulation. I'm going to spend at least 2 slides on EN 285 because that's a very, very important standard that all of you should be exposed to and using it in the industry as you go into your work life. So open now to questions. No questions? Questions? You can ask questions on any of the moist heat sterilization principles that we have covered in the past or I have covered in the session today.
So can you explain the sterilization phases, sir?
Sure. So let me go to this slide because this is more what you're going to see. Okay. So what are the factors which are important for any sterilization, right? There should be no air inside the chamber, right? Because if the air is there, it becomes a deterrent to the sterilization cycle, because when you are trying to achieve a temperature using moist heat, all right, the air will create a pseudo condition of temperature and pressure inside the chamber, which will give a false reading to you. What does this mean? Let's assume that air was present inside the chamber. And now you started to introduce this steam and the air was completely not removed. The air is also going to get heated up. When air heats up, what does it do? It also creates a pressure, right? Now, what do you want to achieve? You want to achieve saturated steam temperature within the chamber at 121 degrees centigrade at the pressure of 1.2 bar. I'm just giving a factor of completely saturated steam, 97% steam, 3% moisture situation from the steam table. 121 degrees centigrade at 1.2 bar is the condition you want to achieve. But if there was air present inside the chamber, the entire chamber is not filled with steam. There is a presence of air which is causing an issue that it has also gone to 121 degrees centigrade by virtue of it coming in contact with the steam and getting heated up. But that air is free from moisture. That air or that section of the gas which is inside the chamber does not have moisture. So is it going to be effective in sterilization? No, because what you need for effective sterilization is moisture. And that moisture is now not present in that small air pocket which is there. And therefore, it is going to cause a pseudo situation where you do not have the right conditions for sterilization. So what is very important is to remove the air from the chamber. That is called as a preconditioning phase. And how do you achieve that? There are two ways of removing air from any chamber. One is you allow the steam to go into the chamber. When you allow a steam to go into the chamber, what is the basic principle of physics? Cold air is heavier than hot air, correct? So when you allow the steam to go in, it kind of displaces the cold air out of the chamber because there is a hotter media and a colder media. Colder media is heavier, it tends to go out to the drain point at the bottom of the autoclave. However, as the progression happens on heating, the air will also get heated up, and as air gets heated up, it gets mixed with a column of steam, and therefore some amount of air is still going to be present. So what do you do if you were not using vacuum as a technique to evacuate air? You will give up steam pressure, you will allow the air to drain out, then you will again pulsate it with steam, you will give pulses of steam so that it kind of displaces the air completely, and you do this multiple times. But it has been found that using that as a technique works for, let's say, vertical autoclaves, smaller size autoclaves. That technique works better because the quantum of air which is entrapped or is present initially in the chamber is low. When you talk about large chambers, 2000 liters, 1500 liters, 1200 liters of air present in the chamber, if you use steam as a means of displacement, then that preconditioning will take a long time. Because what is the method by which you will determine whether the air is removed or not? Bovic test you will do. You will also measure the temperature and pressure at the at the drain point or the coldest spot to make sure that there is completely no presence of air. In such situation, vacuum helps, because what will you do? You will have a chamber, you will put everything inside the chamber, you will apply vacuum. When you apply vacuum, it displaces air into the chamber. Now you allow the that you do it in pulses. So you apply vacuum, allow the system to stabilize or come back to a stable condition, again apply a vacuum, so that you have completely ensured that the air is removed from the system before you start introducing steam. So the vacuum is helping in removing the air from the chamber completely, and then you are introducing steam into the chamber, so that if there is any air, because please remember that no physical equipment, no chamber is 100% leak tight. There is a criteria in EN 285 which says that your chamber has to be leak tight, and there is a criteria given. But all said and done, there is a certain allowable leakage in all kinds of chamber, because there are tolerances, there are machining differences, blah blah blah, as a result of which you will never have a 100% situation of zero air inside a chamber. But vacuuming ensures that you have evacuated maximum amount of air from the system. Then you introduce steam, which also displaces the air from the chamber, and therefore your chances of any air being inside the system are almost reduced to zero, and therefore you do what is called as a pre vacuuming phase. So that is this preconditioning phase which is there. Then you do pre-pressure pulsing. What is the pre-pressure pulsing phase, which is here, is that you introduce a certain amount of steam into the chamber and also combine it with vacuum, so that what are you doing? You introduce steam, so you kind of push the cold air down, and now you applied vacuum, so the vacuum pulled out that air which was somewhere sitting in one corner of that chamber. So pre-pulsing and pre-vacuum as a combination ensures that the air is removed. Now you are sure 100% air is removed. You have to heat up the chamber. You have to heat up the chamber rapidly. So you introduce a lot of steam into the system and you heat it up to 121 degrees centigrade, assuming that that is the condition at which you set your sterilization time, and you achieve 121 degrees centigrade inside the chamber. That is called as that is in the other three-phase system. The vacuuming, pre-pulsing, air evacuation is called as preconditioning phase. The heat up is where it falls as a start of the exposure phase, because you are now starting to heat up the material and expose it to moist heat. So that is the heat up period or the heat up cycle. Once you achieve 121 degrees centigrade, you will allow the system to stabilize that it is at 121 degrees centigrade and 1.2 bar pressure, and that's where your hold time starts. Remember, your sterilization for 10 to the power of minus 6 log was based on what? I will expose the material or the microorganism at 121 degrees centigrade for 12 minutes, 15 minutes, whatever that is. So you cannot start that 15 minutes before achieving 121 and having a stable pressure and temperature. So you allow the heat up to occur, allow the stabilization to occur, meaning it is constant at 121 degrees centigrade or within that tolerance that I spoke a little while ago, and the pressure, and then your hold time starts. So this is where your hold time starts, and this is where it holds. During this period, the temperature and pressure does not go below the set value of 121 degrees centigrade. It may still fluctuate within the tolerance that I spoke about, but the automation and controls are built in so that it never falls below the lowest validated temperature of 121 degrees centigrade and does not go too high. So during that time, there is some amount of steam which may get introduced if the temperature is seen falling, and the temperature will fall because of one simple reason, that there is some amount of condensation which is continuously happening. Remember that chamber is a pressure chamber, but there is a steam trap attached to it. So every time a steam trap opens and lets out the condensate move out of the system, there will be some slight drop in the temperature or the pressure which needs to be built up quickly, and that is why steam pulses are given even during this period, but it is at a constant temperature and pressure held within a tolerant level. Once your hold time is over, then you need to vent it out, you need to remove it out. So initially you allow the steam to or the condensate to move out of the system, and you don't immediately apply vacuum or do not immediately allow it to do it, because remember that it's a pressure vessel. If there is a sudden vacuum which is generated inside the chamber will implode, because it will not be designed for that sudden shock of going into vacuum. So you have to carefully vent it out. So you vent it out, by introducing sterile air into the system. So there's generally a filter, and the filter sucks in air from a clean room. It is a 0.2 micron hydrophobic filter, which allows the air to enter into the system, and at the same time the condensate keeps on going out. So venting happens, so the pressure drops from being a positive pressure to go down. And once it reaches a reasonable value, you start vacuum drying. So you start sucking vacuum from the chamber, applying vacuum to the chamber through a filter, and with a combination of air coming in and a vacuum, what are you doing? You're removing all the moisture within the area from the load which is there, and achieving drying. So this is a methodology where you are doing vacuum drying at a condition where the temperature is falling down from 121 degrees centigrade to a reasonable 40 or 35 degrees centigrade, at which you are now able to remove the load. Because remember that if the material is not cooling down, you can't remove that load, because it will burn your fingers. And remember, the operator is wearing what? He's wearing plastic gloves. Plastic gloves, you try to touch a 80-degree material, what will happen? The plastic gloves will melt. So you don't want that to happen. So you need to bring the temperature down to around 40 degree, ideally 40 degree, which is the exhaust phase or the cooling phase, before which you don't remove the material from the autoclave. That is why you have an aided cycle of vacuum and sometimes jacket cooling to cool down the chamber after the initial venting has happened, so that you can achieve the right drying inside the chamber and the temperature, so that the load can safely be removed without harming the person who is handling it. Okay, so these are the different phases. They are classified into three phases as per the general principle: conditioning phase, exposure phase, and exhaust phase. Or we use more elaborate in the industry, where we define all of these stages, because these are important from a control and automation perspective. When it comes to industry, you are going to define all these phases. When you come to laboratory autoclaves or medical hospital establishment kind of thing, you can just classify them under three broad categories. Is the answer clear now?
Yes, sir. Thank you, sir.
Most welcome. Okay, any other questions? Okay. So if there are no questions, we can end the session for today. Thank you for your attention and time. And we will, I'll see you again tomorrow at 9 o'clock, where we will continue with the type of autoclaves and then jump into the session of principles of FOD and Z value. We will do some basic principles. We will go through the formulae, and we will run through certain examples tomorrow so that you can understand the calculation of FOD and Z value. Again, I will use some examples using certain microorganisms, but in your actual industry applications, you will have to study the microflora and then decide what works best for you and what is the most toughest of the microorganisms that you have to use. And that is why I'm going to bring two different examples, one from the food industry, because there is one organism which is used as an example for studying autoclaving cycles in food industry, and I have brought in that example so that I can demonstrate the different ways of calculating, not different ways, but different conditions at which FO, D, and Z values are achieved. And of course, Geobacillus stereothermophilus is our hero, where we will use that as a biological indicator for doing our calculations in the pharma industry. Okay, so I'll see you all at 9 o'clock in the morning. Tomorrow we will first touch upon the types of autoclaves and then quickly move to the principles of autoclaves. Okay.
Okay, sir.
Right. Thank you very
Thank you,
much,
sir.
and
Thank you,
I'll
sir.
see you all
Thank
tomorrow.
you, sir.
Take care.
Thank you,
Thank
sir.
you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you,
Bye-bye.
sir.